the CMB, obviously. Okay, including the CMB, and also in this object is important the synchrotron photon field that's been emitted by the same electrons. The source of this high enhanced magnetic field and of the emitting particles was proposed to be a pulsar even before the discovery of pulsar in 1967. Here I have the wrong number, the wrong date, by Franco Pacini. And the idea is that the energy, in fact, comes from the slowing down of a fast spinning, highly magnetized neutron star, which in the case of the Crab Nebula is also seen as a pulsar, but this is not always the case. Now, why are pulsar wind nebulae interesting? Well, they're interesting from several points of view. First of all, pulsar physics. Most of the energy that a pulsar loses does not go in direct emission, in direct pulse emission, which is a minor fraction of the total spin down energy. Most of the energy goes indeed in the pulsar wind, which then makes the pulsar wind nebula bright. So they're interesting for pulsar physics. They're interesting from the point of view of plasma physics because they represent the closest and best studied example of relativistic plasmas in the universe. And they're interesting from the point of view of particle acceleration because here we see particle acceleration occurring at the most relativistic shocks in nature with a Lorentz factor of the flow between 10 to the 4th and 10 to the 8th. So much larger even than the GRB's implied Lorentz factors. They're interesting from the, and they're actually gaining more and more interest from the point of view of cosmic ray physics. These are the only sources in which we have direct evidence of PeV particles. PeV particles, PeV is a critical energy for cosmic ray physics. PeV is 10 to the 15 electron volts, and that's where the whole particle cosmic ray spectrum has the knee, the prominent feature known as the knee. So it steepens, and this knee feature is implied to be the place where we see the protons accelerated at the maximum achievable energy in galactic sources. Okay, so the PeV is sort of the maximum energy at which we expect galactic sources to be able to accelerate for protons. In addition, pulsar wind nebulae have been recognized for, let's say, the last 10 years as likely the main contributors of cosmic ray protons at energies above 30 GeV. And they're becoming more and more interesting also for gamma ray astrophysics. They are the most numerous class of galactic gamma ray sources. And they've been found to host extended TV halos, which are a recent puzzle in gamma ray astrophysics and a challenge for gamma ray observations. And again, now that we're starting seeing Pavachon sources in gamma rays, they are a challenge too. We need to get a handle on their physics and on their properties in order to go and look for other possible Pavachons in the galaxy. So when we are looking at the Crab Nebula, what are we looking at? We're looking at a complex system that hosts a number of shocks and discontinuity. So from outside in, we see here the forward shock, the shock launched in the ISM by the supernova explosion that propagates in the ISM, and there is a corresponding reverse shock that propagates in the supernova ejecta. Then behind the shocked and unshocked ejecta, there is the pulsar wind material separated from the ejecta by a contact discontinuity. The pulsar wind material is basically mostly made by by electron-positron pairs and a magnetic field, a toroidal magnetic field wound up around the axis of the pulsar radiation. The the central source of the wind, of course, is the pulsar that launches a highly relativistic wind in its surrounding. But since the wind is confined by the above mentioned contact discontinuity, it has to slow down at some point to match the condition of non-relativistic expansion at the contact discontinuity. And the slowing down occurs at a termination shock, whose position for you can easily estimate based on pressure equilibrium between the wind drum pressure and the pressure in the outer nebula, which for Young's system is easily estimated as E dot, the pulsar spin down power, times the age of the system divided by the volume. When you play this game in the Crab Nebula, you immediately find that the termination shock position has to be at a distance of order square root of V expansion, nebular expansion over C times the nebular radius. And if you go and look at the Crab Nebula at different frequencies around that distance from the pulsar, you see that you see a bright ring that terminates a region, a darker region inside. So it's straightforward to interpret the darker region inside as indeed the cold, non-emitting wind, and the bright ring as the termination shock, at which, together with dissipation, we are now inferring the acceleration of particles that make the emission. So from just looking at the nebula at different frequencies, at the inner nebula, and from simple dynamical consideration, we immediately infer that particle acceleration in the system has to occur at least at optical and X-ray emission frequency at the termination shock. This will be important later. What happens then as time goes by? Well, as time goes by, the pulsar starts to be displaced from the center of the supernova explosion, because pulsars are born with high kick velocities, so they will move away on fast time scales. In the meantime, the reverse shock that was propagating in the ejecta will reach the contact discontinuity and compress the PWN. So the system will undergo some reverberation phase, with the reverse shock reaching some inner radius and then re-expanding. And this is a complex phase to describe, but what's interesting is that during this phase, it might happen that the pulsar has moved far away enough from the center of the explosion, so as to leave a relic nebula and then re-inflate a new nebula somewhere else. At that point, one will have a relic Pulsar Wind Nebula, which will be a bright gamma ray source, because remember, gamma ray emission is due to inverse Compton scattering of relatively low energy particles, say TeV particles, and a displaced X-ray source. So these are the X-ray emitting particles will be higher energy ones, which need to be replenished continuously, whereas these can be relic particles. These are the systems that will be most likely observed in a large number by upcoming TeV telescopes. And in fact, the number of old and relic PWN is expected to increase by a factor of 10 with the next generation Cherenkov telescopes. At even later times, the pulsar will exit the SNR, and at that point, it will find itself in the ISM. And of course, its birth kick velocity is much, much larger than the sound speed in the ISM. So at around 10 to the 4, 10 to the 5 years after leaving the supernova remnant, the pulsar will form a so-called Bauschock nebula, which is a system like this, in which the pulsar wind is now confined not by the supernova remnant anymore, but rather by the run pressure of the ISM that the pulsar sees moving against it at a speed of hundreds of kilometers per second. And these are other interesting systems that we will mention. Now, what is the interesting Pulsar Wind Nebula from the point of view of particle acceleration? When we look at the Crab Nebula and at many similar objects, we usually see this flat spectrum that I was mentioning of low energy particles, the one responsible for radio emission, which then steepens to power law indices that are more common for, say, Fermi-like acceleration, steeper than e⁻², at an energy, at a break energy of order 500 GeV. The highest energy particles in the spectrums are PeV particles, as I was mentioning, in the case of the Crab Nebula. And still in the case of the Crab Nebula, the efficiency with which the pulsar spin-down energy is converted into nebular luminosity almost reaches 30%. So these are extraordinary accelerators. The point is that, however, we don't know how particle acceleration takes place in these objects. All that we know is the flux of energy that leaves the pulsar, which will be made of a magnetic field that we mentioned. The sigma is the so-called magnetization parameter, ratio between Poynting flux and particle kinetic energy. A possible ion component, ion can be stripped of the pulsar surface, and a more abundant electron-positron component. Now here, this is the Goldrake and Julian charge loss rate, which only depends on the magnetic field of the star and on its rotation frequencies. As this kappa here is the multiplicity, the number by which every electron leaving the pulsar is multiplied in terms of electron and positron pairs produced. What we don't know, however, is how this E dot is shared by these different components. And this is very important because since the termination shock is a collisionless shock, the properties, the possible acceleration mechanisms depend intrinsically on the wind composition, whether ions are in the wind, what the multiplicity is, and on the wind magnetization at every single location. The other big unknown is how particles eventually escape the system, which is especially important for cosmic ray physics. What we've learned about the wind, we learned it from numerical modeling mostly. So we learned that the pulsar wind is highly anisotropic. This kind of sin-squared dependence is the dependency of the energy flow. So most of the energy flows in the rotational equator of the pulsar and less towards the pole. In addition, the wind has a region of alternating stripes of opposite polarities due to the pulsar rotation. And this region will extend around the rotational equator of the pulsar for an angled psi, which depends on the relative inclination between the magnetic and rotation axis of the star. In this region here, of course, current sheet develops and magnetic reconnection is not only possible, but even likely when the wind approaches the termination shock. When you plug all these information that you know about the pulsar wind into MHD multidimensional simulations, the first thing you learn is that the termination shock cannot be spherical, but has to be peanut shape. And in addition, so this is half, this is a quarter of the termination shock in projection. In addition, it is highly oblique in several sectors. So the outflow, the flow after the shock will stay mildly relativistic. And this is the origin of these very bright rings that we observe in the X-ray images of Pulsar Wind Nebulae. These are just Doppler boosted features. You can model the emission, you can model the multi-wavelength variability. We did a lot of this modeling in Arcetri. And what we learned from detailed modeling of the emission properties and of the variability of Pulsar Wind Nebulae are important things about the parameters of the pulsar wind that enter the viable acceleration mechanism. The first thing we learned is that the magnetization of the wind on average is large. It has to be larger than 1, actually, on average. And this is an issue because Fermi mechanism, which is the most well-known acceleration mechanism in astrophysics, has a very hard time providing particle acceleration at a magnetized relativistic shock. Although there are some variants invoking turbulence that might help. But the Fermi mechanism in general is an issue. It can only work in the case of Pulsar Wind Nebulae in the low magnetization region that creates in the equatorial plane thanks to magnetic reconnection before and at the termination shock. From modeling of the radio emission, we learned that radio emitting particles do not need to be part of the current pulsar outflow. They could be relic and reaccelerated in the nebula, but by second order Fermi acceleration kind. And this implies that the multiplicity of the wind can be as low as 10 to the 3. And a multiplicity as low as 10 to the 3 also means, based on the equation that I was showing, that the ions might be carrying, if they're there, they might be carrying most of the wind energy, even if the pairs are more numerous. This opens the way to the possibility that acceleration is provided by resonant absorption by the pair of the ion cyclotron waves emitted by the ions. And this is an important possibility to keep in mind when looking at particle acceleration in these systems. It requires that ions be energetically dominant, which is only possible under this condition here. Finally, the multi-frequency variability of the inner region has also told us that actually emitting particles, the highest energy particles, the ones with the steep, the Fermi-like spectrum, must be accelerated in the equatorial region, whereas the lower energy particles can be accelerated anywhere in the nebula, maybe just reaccelerated by the turbulent background. More news about the possibility that ion cyclotron absorption is at work to provide acceleration in Pulsar Wind Nebula came from the recent LASO measurements of the Crab Nebula at the highest energies. If you look at the LASO points, which are these brown things in these plots here, you see that there is a hint of a growth of an increase of the emission towards the highest, the very highest energies, above a PeV. One of the possibilities is to interpret this as the signature that ions are becoming visible through PP emission and consequent by zero decay on top of the inverse Compton dominated leptonic component of the spectrum. We investigated this possibility that ions, the ones with the right spectrum to be responsible for the acceleration of pairs, with oddly enough is a Dirac delta spectrum at the energy of the wind, might be responsible of the emission of these highest energies. But if you go and do the detailed modeling, what you find is that the best fit is found for the ions carrying a very, very small fraction of the wind energy. The bottom line is that indeed, I mean, if you look at the crab right now, the data are consistent with ions possibly being there, but not being energetically dominant in any case. So useless from the point of view of acceleration. More news from LASO measurements are the very recent detection of 12 PeV sources emitting above 100 TeV, implying either leptonic emission by comparable energy electrons or final evidence of hadronic pevatrons, the sources of the highest energy cosmic rays that we've been looking for 100 years. Well, when you go and look at the list of LASO sources, you immediately see that most of them are in coincidence with pulsars. So what happens? Can these all be powered by pulsars and be leptonic in nature? Well, there are two limits on the maximum energy achievable in a Pulsar Wind Nebula. And one holds for Young's system and is the radiation limit on particle acceleration. Particle acceleration time cannot exceed the time for losses, for synchrotron losses, and this sets a limit which is a maximum energy of order 6 PeV for a magnetic field of 100 microgauss. This psi is a parameter that's bound to be less than 1, and it's the ratio between the accelerating electric field and the ambient magnetic field. So young systems like the Crab Nebula can reach PeV energies. For old systems, the most stringent limit doesn't come from radiation losses because fields are typically much lower than 100 microgauss, but rather comes from the pulsar potential drop itself. Now, one might wonder, why is the pulsar potential drop a limitation if I'm doing particle acceleration at the termination shock rather than in the pulsar magnetosphere? Well, if you go and write the pressure equilibrium at the termination shock and estimate the maximum magnetic field that you can get at the termination shock, and plug it into the expression for Emax equal E times accelerating electric field times L, so E times maximum energy times full potential drop at the termination shock, you see that again, the limit is basically set by the pulsar potential drop. It's very simple mathematics, a very straightforward arguments that leads you to conclude that the maximum achievable energy in these systems is 2 PeV with E dot in units of 10 to the 36 ergs per second, and Xi and Xi both bound to be less than 1. If you go and play this game with the Lahasso sources, you see that most sources are actually compatible with particle acceleration in the associated Pulsar Wind Nebulae, with an efficiency which is between 10% and the full potential drop. There is one source, however, that shows particle acceleration exceeding by far, by a factor of 5, the maximum achievable drop. And in this case, I think that the claim is that this is not a pulsar-powered source. Interestingly enough, this source is the source in Cygnus. Cygnus hosts an OB region that has independently implied to be a pevatron in the galaxy, a hadronic pevatron, thanks to powerful the stellar winds or thanks to supernova remnants in the region. But anyway, based on this very straightforward argument, you can already exclude that the Cygnus source is associated with a Pulsar Wind Nebula, and it is likely that this is indeed a hadronic source, since in the galaxy there are basically no other leptonic pevatrons that Pulsar Wind Nebula. Supernova remnants will never be able to accelerate electrons to such high energies because of the much smaller ratio between accelerating electric field and magnetic field. That ratio, I remind you, is bound to be of order V over C, with V the velocity of the flow, which is relativistic essentially only in pulsar-powered systems in the galaxy. Okay.
2 minutes, Elena.
Yes. Okay. So the very last bit that I wanted to mention is this fact here. So Pulsar Wind Nebulae have been implied for now the last 10 years to be the main source of positrons at energies above 30 GeV. The issue with cosmic ray positrons was brought about by Pamela observations of this rising positron fraction, then confirmed by IMS-02 with much higher significance. The rising positron fraction is a problem because until these measurements, we were thinking that positrons are fully secondaries due to the cosmic ray propagation in the galaxy. But if this were the case, the fraction of positrons with respect to the fraction of electrons should decrease with energy. So seeing it rise means that we have sources of positrons, of primary positrons. Of course, one of the candidates is dark matter, and a lot has been written about possible models. A candidate that needs to be taken into account in any case is the contribution of Pulsar Wind Nebulae. We know that these sources produce as many positrons as electrons to 0th order, to a very good approximation. And the same fraction of electrons and positrons is exactly what the data require to be explained. Now, it's interesting that Pulsar Wind Nebulae not only produce the right number, I mean, the same number of electrons and positrons, but their contribution also has the right spectrum to reproduce the positron fraction with the right break at 500 GeV that also helps to explain the break that's sort of observed in spite of the larger error bars associated to the data in the whole lepton spectrum. So Pulsar Wind Nebulae, Bauschock Pulsar Wind Nebulae, the only system from which particle escape is easily accounted, are the best candidate to explain the positron flux. But some doubt was cast on this association by the recent detection of TV halos around systems like Geminga. So Geminga is a bright Bauschock nebula around which a halo of highly suppressed diffusion was detected. Here, particles really have a hard time escaping the nebula, diffusing with a diffusion coefficient which is 100 times lower than the average estimated for the galaxy. Some other Bauschock nebulae instead show completely different features, particle escape that occurs in straight jets perpendicular to the pulsar motion rather than in extended halos. Our group in Arcetri did some work in modeling the Bauschock nebula dynamics, the inner dynamics, and in modeling the escape of particles from Bauschock nebulae. Two interesting results that I just briefly want to mention is that the particle escape is bound to occur in sort of jetted features in generic system, and it becomes progressively more symmetric with increasing energy. Okay, so lower energy particles are more confined in jets, higher energy particles are more isotropically distributed. But the most interesting thing that they found is that particle escape is asymmetric, meaning that positrons and electrons both escape, but along different paths, which means that the pulsar is producing in the surrounding a current. And when you have a current, the number of instabilities that you can excite and that can grow the level of magnetic turbulence increases by far. And so this is a promising way of explaining the halos and assessing how widespread we should expect them to be now that we go and look at the sky with improved gamma ray experiments. Okay, I've reached the end. My summary is that we've learned a lot about Pulsar Wind Nebulae and their dynamics and the properties of the pulsar wind by multi-DMHD modeling. Unfortunately, we still don't know how these sources are such efficient accelerators. We accumulate proofs that they are among the most efficient accelerators in the galaxy, if not in the universe, but we really don't understand how. Yes, I know I'm very late, so I'll let you read the rest and please ask questions if you have any. Thank you.
Thank you, Elena, for the very interesting talk. Let's see if there are questions. I guess there may be many. You can raise your hand or just speak up. Let me see. In the meanwhile, I have a very general question. You mentioned the importance of future gamma ray observatories for this kind of studies. What do you think in particular, I mean, the most important contribution, which open issues are these new instrumentation going to answer, in your opinion?
Okay, so first of all, I think that most of the issues require a combination of theory and observations, but one of the primary objectives of upcoming